The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So, basically, the last few weeks we've been doing derivatives. Now we're going to do integrals. So, okay. So, more precisely, we're going to be talking about double integrals. Okay, so just to motivate the notion, let me just remind you that when you have a function of one variable, say f of x, and if you take its integral from, say, a to b of f of x dx, well, that corresponds to the area below the graph of f over the interval from a to b. Okay, so the picture is something like you have a, you have b, you have the graph of f, and then what the integral measures is the area of this region. And when we say the area of this region, of course, if f is positive, that's what happens. If f is negative, then we count negatively the area below the x-axis. Okay. So now when you have a function of two variables, then you can try to do the same thing. Namely, you can plot its graph. Its graph will be a surface in space. And then we can try to look for the volume below the graph. And that's what we will call the double integral of a function over a certain region. Okay, so let's say that we have a function of two variables x and y. Then we'll look at the volume that's below the graph z equals f of xy. Okay, so let's draw a picture for what this means. I have a function of x and y. I can draw its graph. The graph will be, the surface with equation z equals f of x and y. And, well, I have to decide where I will integrate the function. So for that, I will choose some region in the xy plane, and I will integrate the function on that region. So it's over a region R in the xy plane. So I have this region R, and I look at the piece of the graph that is above this region, and we'll try to compute the volume of this solid here. Okay, that's what the double integral will measure. So we'll call that the double integral over the region R of f of xy dA, and I will have to explain what the notation means. So dA here stands for a piece of area. A stands for area. And, well, it's a double integral, so that's why we have two integral signs. And we'll have to indicate somehow the region over which we're integrating. Okay, we'll come up with more concrete notations when we see how to actually compute these things. But that's the basic definition. Okay, so actually, that's not really much of a definition yet. How do we actually, define this rigorously? Well, remember the integral in one variable you probably saw a definition where you take your integral from a to b and you cut it into little pieces. And then for each little piece, you take the value of a function and you multiply by the width of the piece. That gives you a rectangular slice, and then you sum all of these rectangular slices together. So here we'll do the same thing. Okay, so, well, let me put a picture up and explain what it does. So we are going to cut our region into little pieces, say little rectangles or actually anything we want. And then for each piece, with a small area delta A, we'll take the area delta A times the value of a function in there that will give us the volume of a small box that sits under the graph. And then we'll add all these boxes together. That gives us an estimate of the volume. And then to get actually the integral will be defined as a limit as we subdivide into smaller and smaller boxes and we sum more and more pieces. Okay? So actually what we do, oh, I still have a board here. So the actual definition involves cutting R into small pieces of area that's called delta A, or maybe delta AI, the area of the ith piece. And then, okay, so maybe in the xy plane, we have our region, and we'll cut it maybe using some grid. Okay, and then we'll have each small piece will have area delta A, or maybe delta AI, and it will be at some point, let's call it xi, yi, xi, and then we'll consider the sum over all the pieces of f at that point, xi, yi, times the area of a small piece. So what that corresponds to in the three-dimensional picture is just I sum the volumes of all of these little columns that sit under the graph. Okay, and then so what I do is actually I take the limit as the size of the pieces tends to 0, so I have more and more smaller and smaller pieces. And that gives me the double integral. Sorry, that's not a very good sentence, but whatever. So, okay, so that's the definition. Of course, we'll have to see how to compute it. We don't actually compute it. When you compute an integral in single variable calculus, you don't do that. You don't cut into little pieces and sum the pieces together. So you've learned how to integrate functions using various formulas. And similarly here, we'll learn how to actually compute these things without doing that cutting into small pieces. But okay, any questions first about the concept or what the definition is? Yes? Well, so we'll have to learn which tricks work and how exactly. But so what we'll do actually is we'll reduce the calculation of a double integral to 2 calculations of single integrals. And so for these, certainly all the tricks you've learned in single variable calculus will come in handy. Okay, so yes, that's a strong signal, by the way, that if you've forgotten everything about single variable calculus, now might be a good time to actually brush up on, integrals. The usual integrals and the usual substitution tricks and easy trig in particular. This will be very useful. Okay, so yes, so how do we compute these things? That's what we have to come up with. And, well, going back to what we did with derivatives, to understand variations of functions and derivatives, what we did was really we took slices parallel to an axis or another one. So, in fact, here the key is also the same. So what we're going to do is instead of cutting into a lot of small boxes like that and summing completely at random, will actually somehow scan through our region by parallel planes. Okay, so let me put up actually a slightly different picture up here. So what I'm going to do is I'm going to take planes, say in this picture parallel to the YZ plane. I'll take a moving plane that scans from the back to the front or from the front to the back. So that means, I set a value of x, and I look at the slice x equals x0, and then I will do that for all values of x0. So now in each slice, well, I get what looks a lot like a single variable integral. Okay, and that integral will tell me what is the area in this, well, I guess it was supposed to be green, but it all comes as black. So let's say the black shaded slice. And then when I add all of these areas together as the value of x changes, I will get the volume. Okay, let me try to explain that again. So to compute this integral, what we do is actually we take slices. So let's call S of x the area of a slice through, well, by a plane parallel to the YZ plane. Okay, so on the picture, S of x is just the area of this thing in the vertical wall. Now, if you sum all of these, well, let's see, why does that work? So if you take the region between two parallel slices that are very close to each other, what's the volume between these two things? Well, it's essentially S of x times the thickness of this very thin slice, and the thickness would be delta x, or dx, if you take a limit with more and more slices. Okay, so then the volume will be the integral of S of x dx from, well, what would be the range for x? Well, we would have to start at the very lowest value of x that ever happened in our region, and we'd have to go all the way to the very largest value of x, okay, from the very far back to the very far front. So on this picture, we'd probably start, over here at the back, and we'd end over here at the front. So let me just say from, the minimum x to the maximum x. And now, how do we find S of x? Well, S of x will be actually, again, an integral, but now it's an integral over the variable y, because when we look at this slice, what changes from left to right is y. So, well, let me actually write that down. For a given x, the area S of x you can compute as an integral of f of xy dy. Okay, where now x is a constant and y will be the variable of integration. What's the range for y? Well, it's from the leftmost point here to the rightmost point here on the given slice. So there's a big catch here. That's a very important thing to remember. What is the range of integration? The range of integration for y depends actually on x. See, if I take this slice that's pictured on that diagram, then the range for y goes all the way from the very left to the very right. But if I take a slice that's, say, near the very front, then in fact, only a very small segment of it will be in my region. So the range of values for y will be much less. Let me actually draw a 2D picture for that. So remember, we fix x and we vary, so we fix a value of x. Okay? And for a given value of x, what we'll do is we'll slice our graph by this plane parallel to the YZ plane. So now imagine the graph is sitting above that, and that's the region R. I have the region R, and I have the graph of a function above this region R, and I'm trying to find the area between this segment and the graph above it in this vertical plane. Well, to do that, I have to integrate from y, for y going from here to here. Right? I want the area of a piece that sits above this red segment. And so in particular, the endpoints, the extreme values for y depend on x. Because see, if I slice here instead, well, my bounds for y will be smaller. Okay, so now if I put the two things together, what I will get is actually a formula where I have to integrate over x an integral over y. Okay, and so this is called an iterated integral because we iterate twice the process of taking an integral. Okay, so again, what's important to realize here, I mean, I'm going to say that several times over the next few days, but that's because it's the single most important thing to remember about double integrals. The bounds here are just going to be numbers, okay? Because the question that I'm asking myself here is, what is the first value of x by which I might want to slice, and what is the last value of x? You know, which range of x do I want to look at to take my red slices? And the answer is I would go all the way from here, that's my first slice, to somewhere here, that's my last slice. For any value in between these, I will have some red segment, and I will want to integrate over that. On the other hand, here, the bounds will depend on the outer variable x. Because if I fix a value of x, what the values of y will be depends on x in general. Okay. So I think probably we should do lots of examples to convince ourselves, you know, and see how it works. Sorry. Yeah, it's called an iterated integral because first we integrate over y and then we integrate again over x. Okay? So we can do that, well, I mean, y depends on x or x depends, no, actually x and y vary independently of each other inside here. What is more complicated is how the bounds on y depend on x. But actually you could also do it the other way around. First integrate over x and then over y, and then the bounds for x would depend on y. We'll see that on an example. Yes?
For your y values,
Mm-hmm.
are you using starting points, or are you just using the highest possible range for y?
So for y, I'm using the range of values for y that corresponds to the given value of x. Okay? I mean, remember, this is just like a plot in the xy plane. Above that, we have the graph. Maybe I should draw a picture here instead. For a given value of x, so that's a given slice, I have a range of values for y that is from, you know, in this picture, it's the leftmost point on that slice to the rightmost point on that slice. So where I start and where I stop depends on the value of x. Does that make sense? Kind of? Okay. Okay, no more questions? No? Okay. So let's do a first example. So let's say that we want to integrate the function 1 minus x squared minus y squared over the region defined by x between 0 and 1 and y between 0 and 1. So what does that mean geometrically? Well, z equals 1 minus x squared minus y squared, and it's a variation on, something. I think actually we've plotted that one, right? That was our first example of a function of two variables, possibly. And so we saw that the graph is this paraboloid pointing downwards. Okay, it's what you get by taking a parabola and rotating it. And now what we're asking is, what is the volume between the paraboloid and the xy plane over the square of side 1 in the xy plane, x and y between 0 and 1. Okay, so what we'll do is so see, here I try to represent the square, and we'll just sum the areas of the slices as, say, x varies from 0 to 1. And here, of course, setting up the bounds will be easy, because no matter what x I take, y still goes from 0 to 1. See, it's easiest to do double integrals when the region is just a rectangle in the xy plane, because then you don't have to worry too much about what are the ranges. Okay, so let's do it. Well, that would be the integral from 0 to 1 of the integral from 0 to 1 of 1 minus x squared minus y squared dy dx. Okay, so I'm dropping the parentheses, but if you still want to see them, I'm going to put them in very thin so that you see what it means. But actually, the convention is we won't put these parentheses in there anymore. Okay? So what this means is, first I will integrate 1 minus x squared minus y squared over y ranging from 0 to 1 with x held fixed. So what that represents is the area in this slice. So see here, actually, I've drawn, well, what happens is actually the function takes positive and negative values. So in fact, I will be counting positively this part of the area, and I will be counting negatively this part of the area. I mean, as usual when I do an integral. Okay. So what I will do to evaluate this, I will first do what's called the inner integral. So to do the inner integral, well, it's pretty easy. How do I integrate this? Well, it becomes, so what's the integral of 1? It's y. Just the only thing to remember is we're integrating with respect to y, not to x. Okay? The integral of x squared is x squared times y. And the integral of y squared is y cubed over 3. Okay? And then we plug in the bounds, which are 0 and 1 in this case. And so when you plug y equals 1, you will get 1 minus x squared minus 1/3 minus, well, for y equals 0, you get 0, 0, 0. So nothing changes. Okay, so you're left with 2/3 minus x squared. Okay, and that's a function of x only. Here, you shouldn't see any y's anymore, because y was your integration variable. But you still have x. You still have x because the area of this shaded slice depends, of course, on the value of x. And so now the second thing to do is to do the outer integral. So now we integrate from 0 to 1 what we got, which is 2/3 minus x squared dx. Okay, and we know how to compute that, because that integrates to 2/3 x minus 1/3 x cubed between 0 and 1, and I let you do the computation, you will find it's 1/3. Okay, so that's the final answer. So that's the general pattern. See, when we have a double integral to compute, first we want to set it up carefully. We want to find what will be the bounds in x and y. And here that was actually pretty easy, because our region was very simple. Then we want to compute the inner integral, and then we compute the outer integral. And that's it. Okay, any questions at this point? No? Okay, so by the way, we started with a dA in the notation. Right here we had dA, and that somehow became a dy dx. Okay, so dA became dy dx because when we do the iterated integral this way, what we're actually doing is that we're slicing our region into small rectangles. Okay, now what's the area of this small rectangle here? Well, it's the product of its width times its height, so that's delta x times delta y. Okay, so delta A equals delta x delta y became, so actually it's not just becomes, it's really equal for the small rectangles. For now it became dy dx and not dx dy. Well, that's a question of in which order we do the iterated integral. It's up to us to decide whether we want to integrate x first then y or y first then x. But as we'll see very soon, that is an important decision when it comes to setting up the bounds of integration. Here it doesn't matter, but in general we have to be very careful about in which order we'll do things. Yes? Will always work? Yeah, well, in principle it always works both ways. Sometimes it will be that, because the region has a strange shape, you can actually set it up more easily one way than the other. Sometimes it will also be that the function here, you actually know how to integrate in one way but not the other. So the theory is that it should work both ways. In practice, one of the two calculations may be much harder. Okay. Let's do another example. Let's say that what I wanted to know was, not actually what I computed, namely the volume below the paraboloid, but also the negative of some part that's in the corner towards me. But let's say really what I wanted was just the volume between the paraboloid and the xy plane, so looking only at the part of it that sits above the xy plane. So that means instead of integrating over the entire square of size 1, I should just integrate over the quarter disk, right? I should stop integrating where my paraboloid hits the xy plane. So let me draw another picture. So let's say I wanted to integrate, actually, so let's call this example 2, sorry. So it's the same, we're going to do the same function, but over a different region. And the region will just be now this quarter disk here. Okay, so maybe I should draw a picture in the xy plane. That's my new region R. Okay? So in principle, it will be the same integral, but what changes is the bounds. Why do the bounds change? Well, the bounds change because now if I fix some value of x, then I will want to integrate this part of the slice that's above the xy plane, and I don't want to take this part that's actually outside of my disk. So I should stop integrating over y when y reaches this value here. Okay, on that picture here, on this picture, it tells me for a fixed value of x, the range of values for y should go only from here to here. So that's from here to less than 1. Okay, so for given x, the range of y is, well, so what's the lowest value of y that I will want to look at? It's still 0. From y equals 0 to what's the value of y here? Well, I have to solve in the equation of a circle. Okay? So if I'm here, this is x squared plus y squared equals 1. That means y is square root of 1 minus x squared. Okay, so I will integrate from y equals 0 to y equals square root of 1 minus x squared. And now you see how the bound for y will depend on the value of x. Okay, so while I erase, I will let you think about what is the bound for x now. It's a trick question. Okay. So I claim that what we'll do so we'll write this as an iterated integral. First dy, then dx. And we said for a fixed value of x, the range for y is from 0 to square root of 1 minus x squared. What about the range for x? Well, the range for x should just be numbers. Okay, remember the question I have to ask now is, if I look at all of these yellow slices, which one is the first one that I want to consider? Which one is the last one that I want to consider? So the smallest value of x that I want to consider is 0 again. And then I will actually have a pretty big slice, and I will get smaller and smaller and smaller slices, and it stops. I have to stop when x equals 1. Afterwards, there's nothing else to integrate. So x goes from 0 to 1. Okay, and now see how in the inner integral the bounds depend on x. In the outer one, you just get numbers. Because the questions that you have to ask to set up this one and set up that one are different. Here the question is, if I fix a given x, if I look at a given slice, what's the range for y? Here, the question is, what's the first slice? What is the last slice? Does that make sense? Everyone happy with that? Okay, very good. So now, how do we compute that? Well, we do the inner integral. So that's integral from 0 to square root of 1 minus x squared of 1 minus x squared minus y squared dy. And, well, that integrates to y minus x squared y minus y cubed over 3 from 0 to square root of 1 minus x squared. And then that becomes, well, root of 1 minus x squared minus x squared root of 1 minus x squared minus 1 minus x squared to the 3 halves over 3. And actually, if you look at it for long enough, see this is 1 minus x squared times square root of 1 minus x squared. So actually that's also, so in fact that simplifies to 2/3 of 1 minus x squared to the 3 halves. Okay, let me redo that maybe slightly differently. This was 1 minus x squared times y. So 1 minus x squared times y becomes square root of 1 minus x squared. Oops, x squared. Minus y cubed over 3. And then when I take y equals 0, I get 0, so I don't subtract anything. Okay, so now you see this is 1 minus x squared to the 3 halves minus a third of it, so you're left with 2/3. Okay? So that's the inner integral. The outer integral is the integral from 0 to 1 of 2/3 of 1 minus x squared to the 3 halves dx. And, well, I let you see if you remember single variable integrals by trying to figure out how this actually comes out to be. Is it pi over 2 or pi over 8 actually? I think it's pi over 8. Okay, well, I guess we have to do it then. I wrote something on my notes, but it's not very clear, okay? So how do we compute this thing? Well, we have to do trig substitution. That's the only way I know to compute an integral like that. Okay? So we'll set x equal sine theta, and then square root of 1 minus x squared will be cosine theta. Okay, we're using sine square plus cosine square equals 1. And so that will become so 2/3 remains 2/3. 1 minus x squared to the 3 halves becomes cosine cubed theta. dx, well, if x is sine theta, then dx is cosine theta d theta. So that's cosine theta d theta. And, well, if you do things substitutions the way I do them, then you should worry about the bounds for theta, which will be 0 to pi over 2, or you can, also just plug in the bounds at the end. So now you have the 2/3 times the integral from 0 to pi over 2 of cosine to the 4 theta d theta. And how do you integrate that? Well, you have to use double angle formulas. Okay, so cosine to the 4, remember cosine square theta is 1 plus cosine 2 theta over 2. And we want the square of that. And so that will give us we'll have actually 1/4 plus 1/2 cosine 2 theta plus 1/4 cosine square 2 theta d theta. And how will you handle this guy? Well, using again the double angle formula. Okay, so it's getting slightly nasty. So, but I don't know any simpler solution except for one simpler solution, which is you have a table of integrals of this form inside the nodes. Yes? No, I don't think so, because if you take 1/2 times cosine half times 2, you will still have a half. Okay, so if you do, again, the double angle formula, I think I'm not going to bother to do it. I claim you will get, at the end, pi over 8, because I say so. Okay, so exercise, continue calculating and get pi over 8. Okay, now what does this show us? Well, this shows us actually that this is probably not the right way to do this. Okay, the right way to do this will be to integrate it in polar coordinates, and that's what we'll learn how to do tomorrow. Okay, so we'll actually see how to do it with much less trig. So that will be easier in polar coordinates. So we'll see that tomorrow. Okay, so, but you know, we are almost there. I mean, here you just use the double angle again, and then you can get it, and it's pretty straightforward. Okay, so one thing that's kind of interesting to know is we can exchange the order of integration. So if we have an integral given to us in the order dy dx, we can switch it to dx dy. But we have to be extremely careful with the bounds. So you certainly cannot just swap the bounds of the inner and the outer, because there you would end up, you know, having this square root of 1 minus x squared on the outside, and you would never get a number out of that. So that cannot work. It's more complicated than that. Okay, so, well, here's the first baby example. Certainly, if I do integral from 0 to 1, integral from 0 to 2, dx dy, I can certainly switch the bound without thinking too much. What's the reason for that? Well, the reason for that is, you know, this corresponds in both cases to integrating x from 0 to 2 and y from 0 to 1. It's a rectangle. So if I slice it this way, you see that y goes from 0 to 1 for any x between 0 and 2. It's this guy. If I slice it that way, then x goes from 0 to 2 for any value of y between 0 and 1, and it's this one. So here it works. But in general, I have to draw a picture of my region and see how the slices look like both ways. Okay, so let's do a more interesting one. Let's say that I want to compute integral from 0 to 1 of integral from x to square root of x of e to the y over y dy dx. So why did I choose this guy? I chose this guy because, as far as I can tell, there's no way to integrate e to the y over y. So this is an integral that you cannot compute this way. So it's a good example for why this can be useful. So if you do it this way, you're stuck immediately. So instead, we'll try to switch the order. But to switch the order, we have to understand what do these bounds mean. Okay? So let's draw a picture of the region. Well, what we're saying is y goes from y equals x to y equals square root of x. Well, let's draw y equals x and y equals square root of x. Well, maybe I should actually put this here, y equals x to y equals square root of x. Okay, and so I will go, for each value of x, I will go from y equals x to y equals square root of x. And I will do that for values of x that go from x equals 0 to x equals 1, which happens to be exactly where these things intersect. So my region will consist of all this. Okay? So now, if I want to do it the other way around, I have to decompose my region. The other way around, I have to, so my goal now is to rewrite this as an integral. Well, it's still the same function. It's still e to the y over y, but now I want to integrate dx dy. So how do I integrate over x? Well, I fix a value of y. And for that value of y, what's the range for x? Well, the range for x is from here to here. Okay, what's the value of x here? Let's start with the easy one. This is x equals y. What about this one? It's x equals y squared. Okay, so x goes from y squared to y, and then what about y? Well, I have to start at the bottom of my region, that's y equals 0, to the top, which is at y equals 1. So y goes from 0 to 1. So see, switching the bounds is not completely obvious. That took a little bit of work. But now that we've done that, well, just to see how it goes, it's actually going to be much easier to integrate, because the inner integral, well, what's the integral of e to the y over y with respect to x? It's just that times x, right? From x equals y squared to y. So that will be, well, if I plug x equals y, I will get e to the y, minus, if I plug x equals y squared, I will get e to the y over y times y squared, e to the y times y. Okay? So now if I do the outer integral, I will have the integral from 0 to 1 of e to the y minus y e to the y dy. And that one actually is a little bit easier. So we know how to integrate e to the y. We don't quite know how to integrate y e to the y, but let's try. So let's say, what's the derivative of y e to the y? Well, by the product rule, that's 1 times e to the y plus y times the derivative of e to the y is y e to the y. So if we do, okay, let's put a minus sign in front. Well, that's almost what we want, except we have a minus e to the y instead of a plus e to the y. So we need to add 2e to the y. And I claim that's the antiderivative. Okay, if you got lost, you can also do it by integrating by parts, by taking the derivative of y and integrating this guy. But you know, that works. Just, you know, your first guess would be, maybe let's try minus y e to the y, take the derivative of that, compare, see what you need to do to fix. And so if you take that between 0 and 1, you will eventually get e minus 2. Okay, so tomorrow we're going to see how to do double integrals in polar coordinates, and also applications of double integrals, how to use them for interesting things.